Welcome to Calculus. I'm Professor Greist. We're about to begin Lecture 28 on trigonometric integrals.
We're nearly done with Chapter 3. At this point, we've amassed a large collection of techniques for computing definite and indefinite integrals. In this lesson, what we're going to do is collect all of those methods together and apply them to a particular class of integrals involving trigonometric integrands.
In this lesson, we'll consider three families of integrals involving trigonometric functions. The first, powers of sine and powers of cosine. The second, powers of tangent and powers of secant. The third, multiples of sines and cosines. Throughout, m and n are going to denote positive integers. For our first class of integrals, consider as an integrand sine to the m, cosine to the n. Solving such a problem is going to break up into several different cases, depending on whether m and n are even or odd. This will give us a good chance to practice our various integration techniques. First of all, if you're in the setting where m, the power of sine, is odd, then the following substitution will be effective. Expand sine squared as 1 minus cosine squared, and then substitute in u equals cosine. This will reduce the integral to something that is easily computed. Likewise, if n, the power of cosine, is odd, you perform a similar simplification. Expand out cosine squared as 1 minus sine squared, and then substitute u equals sine. The one remaining case is when m and n are both even. In this case, a substitution will not work. A reduction formula is required. This tends to be a bit more involved and difficult. This is the case that is going to cause us a little bit of trouble. Let's consider a specific example of the form sine to the m, cosine to the n, where m is 5 and n is 4. This puts us in the case where the power of sine is odd. Therefore, we can split off an even number of powers of sine and substitute in 1 minus cosine squared for every sine squared that we have. Now you see that there is one power of sine left over, so that if we perform the substitution where u equals cosine theta, we have a copy of du minus sine theta d theta sitting in the integrand. And we wind up getting minus the integral of quantity 1 minus u squared squared times u to the 4th du. This polynomial can be expanded out and then easily integrated. Substituting back in u equals cosine theta gives us a solution. Negative cosine to the 5th over 5 plus 2 cosine to the 7th over 7 minus cosine to the 9th over 9 plus a constant. Likewise, if we had an odd power of cosine, then we could apply the same method where we substitute in 1 minus sine squared for cosine squared, and we have left over a single power of cosine. Another u substitution will easily solve this integral. Integrals involving powers of tangent and secant follow a similar pattern, depending on the parity of the powers. If one is in the setting where the power of tangent is odd, then perform the simplification, expanding out every tangent squared as secant squared minus 1. Then substitute in u equals secant. Likewise, if n, the power of secant, is even, then one can simplify every secant squared as 1 plus tangent squared. The substitution u equals tangent will then work. the one remaining case where a reduction formula is required is when n, the power of secant, is odd, and m, the power of tangent, is even. Let's consider a specific example, in this case where the power of tangent is 5 and the power of secant is 6. Then, because the power of secant is even, one way to solve this integral is to split off a secant squared and replace the remaining even powers of secant with quantity 1 plus tangent squared. This means that when we do the substitution u equals tangent, we have a copy of du sitting right there to be absorbed. This yields a polynomial integral of the form u to the fifth times quantity 1 plus u squared squared. By expanding that out, integrating that polynomial, and substituting back in tangent for u, we easily obtain the answer: tangent to the sixth over 6 plus tangent to the eighth over 4 plus tangent to the 10th over 10 plus a constant. However, there's another way to solve this integral as well, exploiting the fact that m, the power of tangent, is odd. In this case, what we'll want to do is split off an even power of tangent. Substitute in secant squared minus 1 for tangent squared, and then use the fact that there is a secant tangent left over to perform a substitution where u equals secant theta. There remains in each class that we've considered one case where a simple substitution does not work. This requires a reduction formula. The first step is to simplify to sums of powers of cosine or secant. For example, if we look at the integral of sine to the fourth cosine to the fourth, this is in that one case where both powers are even. We can replace sine squared with 1 minus cosine squared and obtain a sum of integrals, each of which is an even power of cosine. Then we can apply integration by parts twice to obtain the following general reduction formula. The integral of cosine to the n is cosine to the n minus 1 times sine over n plus n minus 1 over n times the integral of cosine to the n minus 2. This simplifies or reduces the level of complexity of the integral involved. Likewise, for powers of secant, one can express the integral of secant to the n as tangent secant to the n minus 2 over n minus 1 plus n minus 2 over n minus 1 times the integral of secant to the n minus 2. Now, you do not have to memorize these formulae. They're the type of thing that one looks up when you're stuck on a difficult integral. Let's apply this reduction formula in the specific case of the integral of cosine to the n. Recalling the reduction formula for powers of cosine, we're going to have to apply this iteratively many times until we get down to a low enough power of cosine that we can proceed. To make things a bit more concrete, let's do a definite integral as theta goes from negative pi over 2 to pi over 2. When we do so, one of the things that's nice is that the term cosine to the n minus 1 sine over n in the reduction formula vanishes when we perform the evaluation. And so, for n greater than 1, we get that the definite integral from negative pi over 2 to pi over 2 of cosine to the n is n minus 1 over n times the same integral with the power being n minus 2. This will allow us to come up with a recursive solution. So let's look at all the different powers. In the simplest case, where n equals 0, well, we can do that integral. The integral of d theta is theta, evaluated from negative pi over 2 to pi over 2 gives pi. Likewise, we can do n equals 1 explicitly, integrating cosine, getting sine, evaluating at the limits gives us the value of 2. Now, for higher powers, we can use the reduction formula. All we have to do is multiply by n minus 1 over n. So to get n equals 2, we multiply 2 minus 1 over 2, that is 1/2, times the integral in the case where n equals 0. To get the value for n equals 3, we multiply the value for n equals 1 by 3 minus 1 over 3. We can continue for increasing values of n, always looking back to n minus 2 and multiplying by n minus 1 over n. Now let's look at this. What do you notice? Well, first of all, it seems as though there's a real dependence on whether n is even or odd. When n is even, there's a factor of pi involved. And when n is odd, there's not. That's maybe not so surprising, seeing that even and odd powers have been different all throughout this lesson. In general, using a little bit of induction, one can show that when n is even, the result of this integral is pi times 1 over 2 times 3 over 4 times 5 over 6, etc., all the way down to n minus 1 over n. When n is odd, one obtains a similar looking result, but starting with 2 instead of pi, and flipping things. The result is 2/3 times 4/5 times 6/7, all the way up to n minus 1 over n. All of that times 2. By putting a 1 down in the denominator, we can see a familiar pattern between these two definite integrals. Now there's one last class of integrals that we're going to look at. That is, something of the form, the integral of sine of m theta times cosine of n theta. The sine wave and the cosine wave have potentially different periods. Now, this integral requires an algebraic simplification. The following formula is something that you do not have to know or have memorized, but which is extremely useful. That is, sine of m theta times cosine of n theta equals 1/2 sine of m plus n theta plus sine of m minus n theta, at least in the case where m and n are not the same. If we integrate both sides with respect to theta, then we obtain the formula negative cosine m plus n theta over 2 times quantity m plus n minus cosine of m minus n theta over twice quantity m minus n. And you can see here why m and n have to be different. Likewise, one can do the same thing for sine of m theta times sine of n theta. A similar reduction gives an integral that is computable. Likewise, with a pair of cosines of different periods, the result works out. Once again, these are not the kind of formulae that you memorize, but they are useful to look up. Now, why would any of these integrals be useful to us? One important reason is that sines and cosines, trigonometric functions, pervade the physical universe. If you go far enough in mathematics, you will learn about Fourier analysis, which is a mathematics built on sines and cosines. It's extremely useful in analyzing any kind of wave, whether acoustic or electromagnetic. In fact, one could argue that all of radar and signal processing is built on a basis of integrals, sines and cosines. Now you know a bit about how to compute them.
I think you'll agree. Some of those integrals were kind of tricky. What do you do when faced with harder and harder integration problems? Do you have to employ ever more clever tricks? No. Mathematics is not about tricks, but rather about principles. However, when having to solve a difficult problem, we have to use every available method. In our next lesson, we'll give a brief introduction to those methods that are computer-assisted.